Today we are going to continue permutations and combinations with the probability. That means, why should I say like that? Because in the probability you must know the knowledge, you must have the knowledge of permutations and combinations also. So today's the continuation topic is nothing but the probability, which is an interesting topic and a most general topic. Everyone can learn this. Everyone can learn this because in the title itself you can see the probable. Probable means possibility. The possibility of the day-to-day events. What are the day-to-day events generally like? It may rain today, if I say. It may rain or it may not rain, we don't know. It's all expectations. India may win cricket against Pakistan, if I say. Then we don't know, it's a prediction. We don't know the exactness of that statement. So, in such a case, to give the mathematical shape to such type of statements which are passed vaguely, that is, which are passed casually. To give a mathematical shape, the mathematician tried to give a formula or rather than a shape to such type of mathematical, such type of statements, a mathematical shape. It was, according to the books, it was given from 16th century, starting from Galileo and till the end of 19th century. It has taken many steps, many changes, and many contributed to the theory of probability, including many Indian mathematicians, and it was given a shape. And in fact, we have, according to our Puranas and all these things, we have this probability right from Mahabharata. And you can see that if you take Shakuni, he used to play gambling with Dharmaraj, and you might be knowing that. So we have that history. India is very rich in mathematics. If you take, we know that theory, and later on this is given a shape mathematically. And let us see now how this can be defined. To begin with, we have the classical definition on probability. If you go through the definition, in a random experiment, if I say in a random experiment, then you might be thinking, what is a random experiment? What is an experiment and what is a random experiment? Let us see that. If there are n number of mutually exclusive, equally likely, exhaustive events, in the first sentence itself, you can find three technical terms. Number one, random experiment. Number two, mutually exclusive. Number three, equally likely. Number four, exhaustive. And all these four are used technically to define the probability, classical definition on probability. So we must know all those four terms before learning the definition. So let me first define you what is a random experiment. First of all, what is an experiment? Generally, for the purpose of definition, it is termed as the experiment. Experiment is nothing but every day-to-day work, what we take up. If you take all of them as experiments and what we conduct, what the works we do, or if they are termed as experiments, among those experiments, what should be the random experiment? That is the important thing here. So, you are throwing a coin, you are tossing a coin, you are throwing a die, you are playing cards, and you are appearing for an IIT JEE examination, and you are appearing for all other examination, even you are appearing for a board examinations, and all these are generally termed as experiment. You can take all of them as experiments. Then what should be the random experiment among all of them? A random experiment is that experiment which can be repeated any number of times, under similar conditions, and all the possible results or outcomes are known to us. All the possible results or outcomes are known to us when the experiment is conducted. And if you conduct that experiment once, then the result or outcome should be one of all the possible outcomes, should be one of all the known possible outcomes. Then only it is said to be a random experiment. For example, simple, I have taken a coin. If you take a coin, Indian rupee coin, on one side you have tail, on another side you have head. Before tossing the coin, the coin is containing head and tail. Before tossing the coin itself, you know that if the coin is tossed, then the outcome or result should be one of the tail or head. This is an important thing you have to understand. So, before conducting the experiment itself, all the possible outcomes. After you conduct the experiment, the result what you get should be one of all the known outcomes. For example, for the better example, I'll tell you, if you take Amitabh Bachchan and Dharmendra, a movie, Sholay, if you take that, and you might be remembering, Amitabh Bachchan has a coin which has both sides head. And he used to use that coin throughout the movie. At last, Dharmendra will be knowing that that coin is containing both sides head. So, but Dharmendra was under the impression that he was under the impression that it's a random experiment. Because Dharmendra is under the impression that it contains both head and tail, but that coin is containing both sides head. Then, according to the assumption of Dharmendra, then it was a random experiment, but it is not a random experiment because the coin is not containing both tail and head. So, understand like that. So, if I prepare a die, generally, the die is a 6-faced die. Then, on each of the faces, 1 point, 2 points, 3 points, 4 points, 5 points, 6 points are marked. Then when we throw the die, either 1 or 2 or 3 or 4 or 5 or 6 comes, isn't it? So if I prepare the die in such a way that the first phase is containing 1, second phase is containing 2, third phase is containing 3, and 4, 5, 6 phases are containing only 4. I know that because I prepared it. Like C.Raghu has his own instruments to play in Mahabharata. You might be knowing that. So similarly, I know that this die has only 1, 2, 3, 4, but 5, 6 is missing. But I am playing with some other person and he is under the impression that this die is containing 6 phases with all the 6 digits, 1, 2, 3, 4, 5, 6. Then in such a case, according to him, it is containing 6 phases, but it is not a random experiment because he knows, he is under the impression that it has 1, 2, 3, 4, 5, 6, but it has no 5 and 6. Then it is not a random experiment. But it can be made as a random experiment if it is revealed to him. If it is revealed to him, we said with him like first phase 1, second phase 2, third phase 3, and remaining all the 3 phases are containing 4. Then it becomes a random experiment. It's fair like that. So, to be more precise and to be more clear, the random experiment is that experiment in which you know all the possible outcomes before conducting the experiment. That is, all the possible outcomes are known to us, and if you conduct the experiment, the outcome or result should be one of all the known possible outcomes. Then only it is said to be a random experiment. Next, coming to the mutually exclusive. What is a mutually exclusive event? You might have learned all this in your board level itself, but you must be more clear in the definition part, because in the questions you might be asked to, on the options you may be given this mutually exclusive, equally likely, simple event, compound event, and all this you might be given. So you must know what all this. Mutually exclusive, the name itself, you have the meaning of a mutually exclusive. That means if I toss the coin, I have got head. There's no question of getting a tail, because occurrence of head is excluding the occurrence of tail. Understand it? So if I throw the die, I have got number 3. I got number 3. Then getting number 3 is excluding the happening of 1, 2, 4, 5, 6. Understand it? That is nothing but mutually exclusive events. What does it mean? No two events in the random experiment occur simultaneously. What does it mean? If I throw the coin, either head or tail comes, but both head and tail never come. That means the occurrence of one event must exclude the happening of the other event. That is why they are said to be mutually exclusive events. Simply, no two events in the random experiment occur simultaneously. That is, occurrence of one event excludes the happening of other events. Okay, that is mutually exclusive. Next, equally likely. In the definition itself, you have all these terms. That is why these are the technical terms you must understand. What are these? Equally likely events. Equally likely, like this, you have the meaning of this word itself will give you the definition. What is equally likely? Tossing a fair coin or unbiased coin. Or simply we can say fair coin. You might have come across this type of terms. What does it mean by unbiased coin? Fair coin. Fair coin means if you take the coin, the surface on the top must be equal to the surface area in the down. That means the surface area on both the sides must be equal. Then it is said to be an unbiased coin that should not have lesser surface area on any one of the sides. So when you toss a coin, equally likely events means the chance of getting head is equal to the chance of getting the tail. Then they are said to be equally likely events. Similarly, if the die is taken, fair die or unbiased die is taken, when you throw the die or when you toss the die, there should be equal chances of occurrence for 1 or 2 or 3 or 4 or 5 or 6. That is nothing but equally likely. You will be better understand if I define the die like this: first phase containing 1, second phase containing 2, third phase containing 3, and 4, 5, 6 phases are containing 4 each, and I defined that now. I defined the die is like this. Then in such a case, the getting 1 and getting 2, getting 3, getting 4 are not equally likely. Because 4 is on 3 phases, there are more chances for 3 to occur when you conduct the experiment. So when you take a fair die or unbiased die, you understand the surface area of the die on 6 phases should be equal. If any surface is more or less, if it is more, the die will settle itself on that side more. If it is less, that will not come on that side. That will be a biased die. And what the example I have given also is a biased die. Unbiased die means there should not be any partiality towards any event to occur more rather than the other. Such events are said to be equally likely events. Okay, equally likely means there are equal chances of occurrence for every event to occur in a random experiment. For example, if you throw the die, how many even numbers are there? 2, 4, 6. How many odd numbers are there? 1, 3, 5. 3 even numbers, 3 odd numbers. 3 even numbers, 3 odd numbers. What does it mean? Getting an even number and getting an odd number in throwing an unbiased die are equally likely, because there are equal chances of getting either odd or even. Then they are said to be equally likely events. Okay. Now you must know this also: simple event and compound event. What is a simple event? Event is simple and it is compound. In the name itself, we have the meaning of it. Simple event means I have thrown a die. Then I ask, I need an odd number. Then, if I need an odd number in throwing a die, I may get either 1 or 3 or 5. That means my wish is split into 3. My event is split into 3. What is it? 1 or 3 or 5. Then such an event is not a simple event, but it is a compound event. Such an event is not a simple event, but it is a compound event. If I ask number 3 in throwing a die, then it cannot further be split. Then in such a case, it is nothing but a simple event. It's nothing but a simple event. Understand? Simple event further cannot be split into 2 or more than 2 events, but compound event can further be split into 2 or more than 2 events. Such events are said to be simple event, means cannot split, and compound event means can be split. Like if you take 52 playing cards, then if I ask you a king, 4 kings are there: diamond king, spade king, heart and king, and clubs king. So 4 kings will be there. That means if I ask king, that king is split into 4 again. So that is nothing but a compound event. If I ask only for a diamond king is only 1, which cannot further be split, which is nothing but a simple event. Understand that? Now, after knowing all these things, very, very important thing, and the basic thing which you must know in the probability is nothing but exhaustive events. Or sample space, or simply total number of outcomes. We can say this as the heart of probability, because if you don't know this, you don't know what is required. So it is very important to understand that you must know the total number of outcomes of any random experiment. So what are they? Let us discuss that in detail before going to the definition. What is it? Exhaustive events or total number of outcomes is nothing but it is simply the list of all possible outcomes. The list of all possible outcomes, or simply we can say it as list of all possible results. So if I throw the coin twice, let us take thrice also. If I throw the coin once, it is nothing but either head or tail. Once it is either head or tail. If I throw the coin twice, it is HH, HT, TH, TT. It is 2. You can understand it is 2 square. If I throw the coin thrice, head, HHT, HTH, THH, TTH, THT, HTT, all T's. So how many outcomes do we have here? This is 4 plus 4, 8. It is nothing but 2 cube. So the base is nothing but when you conduct the experiment once, the number of outcomes are 2. As many coins as you use, that goes to the power. If you are using 2 coins, or if you are conducting this experiment twice, or if you are using 2 coins, that number goes to the power. This should always be the base. So this is 2 square. 3 coins are used, 2 cube. 4 coins are used, 2 power 4. And 5 coins are used, 2 power 5. And n coins are used, it is 2 power n outcomes will be there. This is important thing you have to understand. And if you take die, what should be the die? Die contains 6 numbers. They are nothing but 1, 2, 3, 4, 5, 6. So 6 will be there. And if I take 2 dice and if I throw 2 dice, or if I throw the die twice, both are same. If I throw 2 dice, or if I throw the die twice, then if I count the possible number of outcomes, then again the principle of counting. This is a basic thing you can understand. Principle of counting. When the die is thrown twice, there will be 2 outcomes. That is first die, second die, or first time die thrown, second time die thrown. So this can be filled in 6 different ways, either 1 or 2 or 3 or 4 or 5 or 6, and the second one also can be filled in the same way, 6, 1 or 2 or 3 or 4 or 5 or 6. It is nothing but 6 into 6, it's nothing but 6 square. So when 2 dice are thrown, it is 6 square, the number goes to the power. Like what it is, 1 1, 1 2, and so on, 1 6, and so on, 6 6. Like this, you will get totally 6 square outcomes. If 3 dice are thrown, you can understand it becomes 6 into 6 into 6. It is nothing but 6 cube. So basing on principle of counting only, we will be doing all these things. So you need the basic knowledge of the permutations and combinations also to solve the problems related to probability. So the exhaustive events or the sample space, generally it is denoted by S. The sample space is denoted by S, or the exhaustive events or the total number of outcomes is nothing but simply the list of all the possible outcomes. Like if you take the 52 cards, playing cards, then how many outcomes will be there in 52 cards? 52 will be there. If 2 such pack of cards are taken, then you're mixing it up, then how many will be there? Then you think of it like that. So without knowing the total number of outcomes, the problem cannot be solved. Understand that. So what are the terms we have seen now? Random experiment, mutually exclusive events, equally likely events. Of course, I have defined simple event and compound event also. And then finally, which is very, very important one, is the sample space or the exhaustive events is nothing but the list of all possible outcomes. So if you know all these things, then we can go to the classical definition on probability. You can see that in a random experiment, if there are n number of mutually exclusive, equally likely, exhaustive events, and for an event A to occur, if there are m number of favorable outcomes, then the probability of occurrence of event A is defined to be P of A is equal to m by n, which is the classical definition on probability. But you understand this can be used under all these restrictions only. What are the restrictions here? Just it should be a random experiment. They must be equally likely, mutually exclusive events. For an event A to occur, P of A is given to be m upon n, which is nothing but number of favorable outcomes whole divided by total number of outcomes. Okay, which is known to be m upon n. For an event A to occur, there are m favorable outcomes and the total number of outcomes are n. Then for the event not to occur, negation. The event not to occur, that is P of A bar, or it can also be denoted as P of A complement. Both are same. The total number of outcomes are n and the favorable outcomes to A are m, then the non-favorable outcomes to A, non-favorable outcomes to A are nothing but n minus m upon n. Okay, then if you split it, it is n by n1 minus m by n, that is P of A. M by n is nothing but P of A. Now what is it? P of A bar. So you can understand that from this one, P of A plus P of A bar is equal to 1. P of A plus P of A bar is equal to 1. That is the sum of the probabilities of occurrence and non-occurrence of an event is always equal to unity. Understand that. It will never exceed 1. That means probability will never be negative and the probability will never exceed 1. That means it always lies between 0 and 1. It is clear that because the numerator is contained in the denominator. Numerator is contained in the denominator. That is why numerator will always be less than the denominator or equal to the denominator. Then it will never exceed 1. That is why the value of probability always lies between 0 and 1. 0 less than or equal to P of A less than or equal to 1. Okay, generally this P of A is equal to 0 is termed as the impossible event. And P of A is equal to 1 is said to be certain event. P of A is equal to 0 is an impossible event means what? The event never occurs. Generally, in the day-to-day life, P of A is equal to 0 and impossible event means P of A is equal to 1 is certain event means we can frame the problems in such a way that the probability is 0, the probability is 1. If you take the nature, if you take all the experiment what we are performing in day-to-day life, generally nobody will have certain event. Certain event like what? An impossible event. Like if I say the sun rises in the west, then it's impossible because it is everybody knows that the sun rises in the east. If I say some boy I have taken, Rahul Gandhi is a girl, if I say, you will not accept because it's a natural truth that he is a boy, then in such a case the probability becomes 0. Generally, probability becomes 0, probability becomes 1 is generally attributed to natural truths only. Our life always fluctuates between 0 and 1. Because if you know that, you will get into IITs, definitely you will never listen to my lecture. You will never sit in the class if you are certain that you are going to get seat in IIT. Okay, then in such a case, what happens? Human life always fluctuates between 0 and 1. This is the beauty of probability. Okay, now according to the classical definition, what we understood here, you must know the total number of outcomes, whatever the problem you take up, and in that one you must know the total number of outcomes, and from this one you have to pick out the number of favorable outcomes, you place it in the numerator and the total number of outcomes in the denominator, and thereby you will be getting the probability of the occurrence of a certain event A. Okay, so is equal to 0 is impossible event, is equal to 1 is a certain event, and the probability value whenever you find out, it should never be negative and it should never be greater than 1. If you get such type of answer which is not lying between 0 and 1, you make yourself sure that you have gone wrong in simplifying the problem. So its value must always lie between 0 and 1, either it is equal to 0 or it is equal to 1, like that. Okay, now after many researches and after many correspondence between many mathematicians and all, the probability is given a certain shape with the introduction of set theory. With the introduction of set theory, that is nothing but axiomatic approach. What is axiomatic approach? The definition, what it is given in the classical definition, that is given axioms. You might be knowing what are the axioms. Axioms are the rules or principles given by the mathematician without any proof. You have to accept. So here, axiomatic approach to define the probability. F maps, the power set of S is nothing but a sample space, to the real number set R is said to be a probability function. Is said to be a probability function if it satisfies the following three axioms. What are they? Number one, axiom of positivity. What does it mean? It is given a name. Just now I discussed. What is it? The probability will never be negative. It should always lie between 0 and 1. That's what is named as axiom of positivity. Means P of A should always be. I can say axiom of positivity or axiom of non-negativity. You must say exactly. It should be axiom of non-negativity. Non-negativity means it will never be less than 0. So P of A should always be greater than or equal to 0. That is nothing but axiom of positivity. Number 2, axiom of certainty. This is another name given for random experiment. What is a random experiment? You must know all the possible outcomes. That is, if you take the probability of the sample space, it should always be 1. That means all the possible outcomes are known to us. So axiom of certainty means probability of sample space is 1. In other words, it is nothing but you must know all the possible outcomes whenever an experiment is conducted. Whenever an experiment is conducted. Number 3, axiom of union. What is axiom of union? P of A union B is equal to P of A union written as plus P of B only when A and B are disjoint sets. Understand? What is the meaning of disjoint set? There should be nothing common to both the sets A and B. There you must not have anything common to both the sets A and B. Then only they are said to be disjoint sets. Like if I ask you to collect the coefficients of 2 from 1 to 20. From 1 to 20, if I ask you to collect the coefficients, then it is 2, 4, 6, 8, 10, and so on up to 20. If I ask you to collect the coefficients of 3, then it is 3, 6, which is common to 2. Again 9, next to 12, which is common to 2. Then they are not disjoint sets. They are not disjoint sets. So disjoint sets are those sets that should be there should not be anything common to both the sets. Then this is said to be the axiom of union. When there is something common, then how to apply this axiom of union, which is nothing but the addition theorem. Understand it please carefully. Addition theorem is based on the axiom of union only. So addition theorem is P of A union B is equal to P of A plus P of B minus P of A intersection B. Why should it be P of A intersection B? If you see through the Venn diagrams, it is sample space S, this is A, this is B. If I say, and this is A horizontally, this is B vertically, this is nothing but A intersection B, then if I write axiom of union for this one directly, like P of A plus P of B, what will it be? What happens? These two are not disjoint sets. You cannot apply that. The reason is, when you take P of A and written here, and plus P of B and written here, this is counted twice. It's clear. It's counted twice. That is why it is subtracted. Very simple. That is why it is subtracted. What is intersection? Common area. Common area is subtracted. This is nothing but the addition theorem on probability. Okay. Now, let us see the problems based on the classical definition on probability before going to the next part, which is the conditional probability. Okay. See the first problem now. 6 married couples are standing in a room. 6 married couples are standing in a room. Couples, doubles. It is 6 into 2, 12. 12 persons are there. And if 4 people are chosen at random, then the chance that exactly one married couple is among the 4 is exactly one married couple is among the 4 is. So, whenever you attempt any problem in probability, don't forget to write the total number of outcomes. If you are clear about the total number of outcomes, then you can pick out your favorable number of outcomes. So, before solving any problem on probability, don't forget to write the total number of outcomes, or in other words, exhaustive events, or it is nothing but the sample space. So, from now onwards, I'll be using this. P of A is equal to N of E upon N of S. Probability of an event A is nothing but number of favorable outcomes to A whole divided by total number of outcomes in the sample space. Total number of outcomes, simple. So, N of E upon N of S. So, before writing the probability, let me write first N of S. What is N of S? The total number of outcomes. How many people are there? 6 married couples are there. 6 married couples means it is 6 into 12. 12 people are there. From 12 people, how many people are chosen? 4 people are chosen. Choosing is nothing but. And I want to tell you, the choosing or the selection is nothing but a combination. It's nothing but a combination. Arrangement is nothing but a permutation. So, 12 people are there. From 12 people, 4 are taken. It is 12C4. It is 12C4. The total number of outcomes will be 12C4. 12C4 means all the 4 may be males, all the 4 may be females, and 2 may be male, 2 may be female, and 1 may be male, 3 may be female. Like that, many number of combinations may be there. The total number of combinations are 12C4. But what is a restriction given there? Among the 4 people chosen at random, then the chance that exactly one married couple among the 4, you must have only one married couple. So, how many married couple are there? 6 are there. 6 are there. So, what I do, I'll take, that is, I'm writing N of E now. This is N of S written, that is denominator written first. N of E I'm writing. Now, what I do, because I need only one married couple, there are 6 married couple are there, I'll choose one from 6. I have chosen. This is the first operation I am performing. I've been repeating. Whenever you are solving the problems based on permutations and combinations, and now probability, always split the problem into operations. You will be more comfortable in solving the problem. So, first operation, what I performed, I have chosen one married couple from the 6. 6C1 did. And what should be the second operation? Second operation, I need 2 more. So, how many are remaining now? How many are remaining? Here, one couple is taken from 12, 2 are taken, 10 are remaining. From 10, I'll take 2. Alright, this one is nothing but a couple. So, 2 are taken. Total, how many persons are there? 12 persons are there. From 12, I have taken 2. How many are remaining? 10. But I have taken only 2. I need 2 more. That is why those 2 are taken from 10 to 10C2. But what happens? Among this 10C2, you may be getting 1 male, 1 female, 2 males, 2 female. Like that, different combinations you may be getting. But I need only exactly one married couple. This one only I need. So, what I don't need, second married couple, I don't need that combination. So, because one married couple is already chosen, how many married couples are remaining? Only 5 are remaining. Those 5 I don't need because I have already chosen. So, this 10C2 contains, because it is 2. The tendency to contain, there are possibilities of getting again a married couple which we don't want. That is why that is to be subtracted. What is 5C1? Because from 5 married couple I can choose 1. So that is subtracted because we don't want that. First operation performed, second operation performed, and these two operations one after the other simultaneously can be performed in 6C1 into 10C2 minus 5C1, which is nothing but 6 into, it is 10 into 9 upon 2, it is nothing but 5 into 9, nothing but 45, I'll write that directly, 45 minus 5, which is nothing but 6 into 40 is nothing but n of E. Therefore, P of E is equal to n of E upon n of S. I have already written the formula there. So, it is nothing but 6 into 40 upon 12C4. You can simplify that, and while simplifying, don't apply the factorial, never apply, it will be waste of time. So because suffix is 4, write only 4 factors, 12 into 11 into 10 into 9 upon 4 into 3 into 2. Reverse this, reciprocal of this, simplify, you will get the required probability. So what the approach in solving the problem is important. What is the approach? I taught you. First of all, don't forget to write the total number of outcomes. After writing the total number of outcomes, think of the favorable number of outcomes. Favorable number of outcomes are like this. We need only 1 married couple. We have taken already. And how many should be taken again? Like 2 persons are to be extra to be taken. From 10 remaining 10 I have taken 2. But this tendency contains again 5 married couple. There are chances of getting married couple again, but I need only exactly 1 married couple. That is why I have subtracted it, and this will give you a favorable number of outcomes, and favorable number of outcomes divided by total number of outcomes will give you the required probability. Okay, go to the next slide. There are 4 defective items in a lot consisting of 10 items. From this lot we select 5 items at random. How many items are chosen? 5 items are chosen at random. The probability that there will be 2 defective items among them is. Understand that, please. Understand that carefully. Now, let us write. The formula is one and the same. P of A is equal to N of E upon N of S. I need the total number of outcomes, N of S. How many items are taken? How many total number of items are there? First of all, you see that there are 4 defective items in a lot consisting of 10 items. So, how many total number of items are there? 10 total number of items are there. How many items are taken? 5 items are taken at random. Go through the problem, please. See the problem. Read that. So, 5 are taken. Total number of items are 10. So, from 10, 5 are chosen. So, 10C5. That lot is consisting of 10 items, and from 10 I have taken only 5. It is 10C5. Now, I have got the total number of outcomes. From this one, what we need is there is 4 defective items in the lot and 6 non-defective items. 4 are defective and 6 are non-defective. Let us suppose there are 10 apples. Among 10 apples, 4 are bad apples or rotten apples, and 6 are good apples. Now, how many ways the apples can be chosen? They can be, total number of outcomes will be 10C5. This 10C5 may be contained, you may get all the 4 bad apples, like rotten apples, and you may get 1 rotten, 4 good. You may get 2 rotten, 3 good. Like that, different combinations you will be getting, the total number will be 10C5. But here, the question is the probability that there will be 2 defective items among them is. He needs exactly 2 defective items. So, how many defective items are there? You can go through the beginning of the problem. 4 defective items are there. From 4, how many can be chosen? How many should be chosen? We need 2 defective. For C2, first operation performed, that is restriction fulfilled. And how many are remaining now? 5 are taken. So, among 5, already 2 are taken. How many are remaining? 3 are remaining. How many are remaining? 3 are remaining. Those 3 must be non-defective. Those 3 must be non-defective. How many non-defective are there? How many non-defective are there? 10 minus 4, 6. So from 6, you have to take the remaining 3. First operation performed in 4C2 different ways, getting 2 defective items exactly. And second operation getting 3 non-defective items from the 6 non-defective items. Second operation performed. Principle of counting that we multiplied. So this is a favorable number of outcomes, and the total number of outcomes are this. Therefore, let me say this as A. Never mind. This is P of A is nothing but 4C2 into 6C3 upon 10C5. You can of course simplify this directly. Improve mind calculation instead of applying the factorials and all. Improve mind calculation. 4C2 is nothing but 4 into 3 upon 2. 4 into 3 upon 2 means 2 into 3. 6 into 6C3 is nothing but 6 into 5 into 4 upon 6. 6 is getting cancelled. 5 4s are 20. Upon 10C5, what I said, you have to write 5 factors starting from 10. 10 into 9 into 8 into 7 into 6. And denominator comes to the numerator 5 into 4 into 3 into 2. If you simplify this, you'll be getting required probability. In the similar problem, just to try this similar problem, how it can be seen. Please go forward. In a batch of 10 articles, please go through that. It is your homework. In a batch of 10 articles, 4 articles are defective. 6 articles are taken from the batch for inspection. 6 articles are taken from the batch for inspection. If more than 2 articles in the batch are defective, the whole batch is rejected. Whole batch is rejected. And find the probability that the batch will be rejected. Of course, it requires little more knowledge, but try that because you have already learned the concepts in the board level. You can try that problem. What is it? In a batch of 10 articles, 4 articles are defective. In a similar way, 4 articles are defective means 6 articles are good. Then the 6 articles are taken from the batch for inspection. How many are taken? 6 articles are taken from the batch for the inspection. If more than 2 articles in the batch are defective, from the 6, if more than 2 are defective, then the entire consignment will be cancelled or rejected. So what is the probability of rejecting the consignment or that articles?